Okay, we want to interpret each of these in terms of the motion of a pendulum. We can imagine that we've got a pendulum oscillating not in air, because the drag coefficient is going to be really low in air. So for most pendulums, you're never going to get a gamma high enough to make this zero. So we put it in water, and it oscillates. Okay? Yeah, but it still doesn't oscillate like this or like this. No, nothing we can do will make it do exactly this or exactly this. Okay? So we start adding molasses. Okay? And we keep adding molasses until we get this can get this behavior or this behavior. How are we going to recognize when we have this behavior? How are we going to recognize when we have this behavior? Well, if this is a graph of position versus time, which it is in this interpretation, okay, then in general we're going to have some mix of these two with arbitrary constants depending on what we do to that pendulum, right? If we have just purely this, and we don't bother putting a constant on it because that wouldn't make any difference except in our amplitude, okay? The behavior is going to be the same. Then we would have x1 of 0 equals 1, right?
Right.
Okay, so here's a pendulum. There's no pendulum there. You're going to draw the pendulum, right? And here's x equals 0. This is the equilibrium position, right?
Right.
Is the pendulum here at time t equals 0?
No.
Where is it?
It's X.
Draw the picture.